This is a walkthrough of Problem 2 on Exam 2 of Module 9 in the book Problem Solving Guide for Electromagnetism and Optics. We have a regular hexagonal wire frame, side length 5 centimeters, has an electrical resistance of 0.1 ohms, has a constant counterclockwise current of 20 milliamps flowing around it due to the changing magnetic field. At t equals 0, the magnetic field has a magnitude of 200 millitesla directly out of the page and is changing at a constant rate. Write an expression for the external magnetic field as a function of time. That is, what is B of t? Let's start by indicating the direction of the magnetic field at t equals 0. It's out of the page. The current is counterclockwise. Current's going that way. The area of the loop isn't changing, but we have to calculate it because it belongs in the B times A equation. A regular hexagon is composed of 6 equilateral triangles. In this case, each side is 5 centimeters. Each of those triangles has an area of 1/2 base times height. The angles are all 60 degrees, so we can write sine of 60 is the opposite side, which is the height, divided by the hypotenuse, which is 5 centimeters. They're all the sides are 5 centimeters. So we can calculate the height, and we can calculate the area of one triangle, 10.825 square centimeters. The area of the hexagon is 6 of those, which is 64.95 square centimeters, which is 0.006495 square meters. Now we can focus on how the magnetic field is changing. The EMF in the loop, which is producing the current, is IR. I is 20 milliamps, 0.02 amps. The resistance is 0.1 ohms, so the EMF is 2 millivolts, 0.002 volts. This is the rate of change of the magnetic flux. D flux dt. The flux is B times A. The area is constant. We have to put it in there. And then we have this dB dt, which is what we need for the equation. How quickly is the magnetic field changing? We can solve this for dB dt. It's 0.002 volts divided by the area, and that's 0.308 Tesla every second in SI units, which is 308 millitesla per second. But is it increasing or decreasing? If you look at the direction of the current in this part of the hexagon, we can put our thumb of our right hand in the direction of the current and curl our fingers around. Inside the hexagon, it's coming out of the page. If it's adding to the field must be decreasing. So we know the magnetic field is shrinking. So now we can get the equation. It starts off at 200, decreases 308 millitesla every second. So the equation is 200 millitesla minus 308 millitesla per second times t. That's problem 2.